Hi, I'm Sarah. I'm a PhD student at Liverpool John Moores University, and I'll be talking about red supergiants in M31 and the Humphreys-Davison limit. So just some brief background. Humphreys-Davison limit is the empirical upper limit to red supergiant luminosity. And here you can see in the plot from the original 1979 paper by Humphreys and Davison, there's a lack of red supergiants observed past a certain point. So this limit is thought to be caused by mass loss from rotatively driven winds on the main sequence, causing the most massive stars to lose too much envelope and divert away from the cool side of the HR diagram. However, mass loss rates depend not only on mass, but also on metallicity, where more metal-rich stars will have stronger winds. So this means that if the HD limit is caused by mass loss from these winds, then we'd expect to observe a lower limit for higher metallicity galaxies. So this limit was first estimated to be around 5.8. However, more recent observations of the SMC and LMC show a revised limit of approximately 5.5 for both galaxies. And this is despite a difference in metallicity of around a factor of 2. So in this work, we expand to a higher metallicity and look at the HD limit with the study of the red supergiant population of M31. We do this by compiling a sample of red supergiant candidates using the Spitzer mid-infrared M31 survey, making mid-infrared cuts around the sample of known optically selected M31 red supergiants. We then cross-match these objects to optical and near-infrared catalogues, where we can make further cuts to optical colours and proper motion to screen out any bluer objects and foreground stars. And this leaves us with a sample of approximately 400 red supergiant candidates. We then integrate under the de-reddened spectral energy distribution of each red supergiant candidate to obtain bolometric luminosity. And these are the SEDs of some of the brightest objects that we find. And these are really important to the high end of the M31 red supergiant luminosity function, which looks like this. And this just shows the number of red supergiants in M31 per log luminosity bin. And here I flagged one object just because it is a borderline candidate and is on the cusp of being a foreground object. So we can't definitively rule it out, so we do keep it in our sample. But here we've got overplotted the Geneva evolutionary model predictions from population synthesis. And at first glance, they don't look too bad, maybe over-predicting a few more brighter stars compared to our observed distribution. However, we are dealing with low number statistics, which I'll touch on a little bit later. But what we can note so far is that our HD limit doesn't appear to be lower than the LMC and SMC, which is already in tension with a prediction of a metallicity dependent limit. So we then looked at the cumulative distributions of our observed red supergiant luminosities for the LMC, SMC, and M31. And we can see they look similar in shape. But to quantify this, we perform a KS test to compare the distributions, where we find for M31 compared with the SMC, a 60% probability of being drawn from the same parent distribution, and 44% for M31 compared with the LMC. So here we can't rule out these observational luminosity functions are drawn from the same parent distribution. So we then do the same for the model cumulative distributions to see how they compare with observation. So here we have the solar models and what the Milky Way, or roughly M31, should look like. And we also have the SMC-like models here. And we do another KS test, this time between the observed and modelled distributions, where we find these really low probabilities for M31 and even lower for the SMC. So these are unlikely to have been drawn from the same parent distribution. So what we're seeing is that the models predict there should be a difference between the red supergiant luminosity functions of M31 and the SMC. However, we don't see that, which suggests that the luminosity functions of red supergiants may not be metallicity dependent. So we've seen that the models predict our LMAX should be between 5.7 and 5.8 for M31. We're seeing something more like 5.5 in observation. And because we have very small numbers at the high luminosity end, we have stochastic effects where the LMAX we expect to find is a function of our sample size. So in other words, the larger the sample size, the higher the probability of sampling close to the true Humphreys-Davison limit. So we investigate how LMAX changes with sample size using a Monte Carlo simulation, where we randomly select n stars from the theoretical luminosity function and determine the LMAX of that sample. And we repeat this 10 to the 5 times to find the average LMAX for each sample size of n. And the result of the Monte Carlo at M31-like metallicity looks like this. And here we can see the LMAX that we'd expect to measure, plus the confidence intervals of that value as a function of sample size. And we can see how this fares against our observed LMAX and sample size for M31. Which is indicated here by the black star. And we can see that there's this slight disagreement with model prediction at the 2 sigma level. And this is what we get for the SMC. This time we can see that the disagreement is beyond 3 sigma. So there's this clear discrepancy between observation and model predictions for the Humphreys-Davison limit, which gets worse at lower metallicities. So to summarise, the luminosity function of red supergiants is independent of metallicity based on the range that we've studied. Lmax is also independent of metallicity, where we find the Humphreys-Davison limit for M31 is again approximately 5.5, much like for the SMC and the LMC. So we're not finding this metallicity dependence that is predicted. And this is really important because it tells that the main cause of the Humphreys-Davison limit is not mass loss due to hot star winds on the main sequence, as previously thought. Thanks for listening.